Right now, your phone can tell you where you are within a few meters, anywhere on Earth. It feels mundane, but it only works because of one of the strangest ideas in all of physics. That time itself runs at different speeds depending on how fast you move and how strong the gravity is. Your Maps app is quietly running on Einstein's relativity. Here is how. GPS was not built for you. It began in 1973 as a United States military project, born of the Cold War need to guide ships, aircraft, and missiles precisely. Its ancestor, a system called transit, had tracked submarines using the Doppler shift of a satellite signal. GPS was the far more ambitious successor, and it would not be fully complete until 1995. Today, the system is a constellation of about 31 satellites, each orbiting some 20,000 kilometers up, roughly 12,000 miles. Every one carries an atomic clock, so precise it would lose less than a second in 100 million years. They do nothing but broadcast, endlessly, the exact time and their exact position. Your phone simply listens. An atomic clock keeps time not by a swinging pendulum, but by the atom itself. A cesium atom flips between two energy states at an utter fixed rate of 9 billion times a second. Counting those flips gets ticks so steady that, since 1967, the second itself has been defined by it. This is the most reliable rhythm humanity has ever found. Timing. Each satellite signal carries the exact moment it was sent. Your phone notes when it arrives, and the tiny delay reveals how far away that satellite is. The signal travels at the speed of light, so distance is just that delay multiplied by light's speed. The whole system is really an extraordinarily precise way of measuring time and turning it into distance. 1 distance places you on a sphere. 2, and you are on a circle. 3 pin you to a point almost. The catch is that your phone's own cheap clock is not perfectly synced to the satellites, so a 4th satellite is brought in, and its extra measurement solves for that clock error at the same time. 4 signals give you position and perfect time together, and timing this precisely is brutally unforgiving. Light and the radio signal travels about 30 centimeters, 1 foot, in a single nanosecond, a billionth of a second. So if the clocks are off by even a few billionths of a second, your position is off by meters. To work at all, every clock in the system must agree to the nanosecond, and that is where the trouble starts. In 1905, Albert Einstein published special relativity, and with it a fact that defies all common sense. Time is not absolute. A clock that is moving ticks more slowly than one at rest, not from any mechanical fault, but because time itself, for the moving clock, genuinely passes slower. For most of human history, this was far too small to ever notice. GPS notices. Special relativity broke something we never questioned, the idea of a single, universal now. Einstein showed that 2 events one observer calls simultaneous, another moving observer does not. There is no master clock for the universe, ticking the same for everyone. Every clock keeps its own time, set by its own motion. GPS has to reconcile dozens of these disagreeing clocks in orbit and on the ground. The GPS satellites race around the Earth at about 14,000 kilometers an hour, roughly 9,000 miles an hour. By special relativity, that speed makes their onboard clocks tick slightly slower than clocks on the ground. The effect is tiny, about 7 millionths of a second lost every day. Tiny, but for a system that lives or dies by the nanosecond, it is enormous. But there is a second effect, and it pulls the other way. In 1915, Einstein's general relativity revealed that gravity also slows time. The stronger the gravity, the slower the clock. Down on Earth's surface, deep in the planet's gravity well, our clocks run slow. Up where the satellites orbit, gravity is weaker, so their clocks tick faster than ours do. So the satellites face 2 opposite pulls on their clocks. Their speed makes them run about 7 microseconds slow each day. But their high, weak gravity orbit makes them run about 45 microseconds fast each day. Gravity wins. Add the two together, and a GPS clock gains about 38 millionths of a second every single day compared to the ground. 38 microseconds sounds like nothing. You could never feel it. But remember, light travels a foot every nanosecond, and 38 microseconds is 38,000 nanoseconds. Left uncorrected, that timing error would throw your position off by about 10 kilometers over 6 miles every single day. Within minutes of switching on, GPS would be useless. The engineers knew this before the first satellite launched, so they built the correction directly into the system. The atomic clocks were deliberately tuned before launch to tick at a slightly wrong rate on the ground, so that once in orbit with relativity speeding them up, they would settle to exactly the right rate. Einstein's equations are, quite literally, machined into the hardware. There is a story that not everyone trusted the theory. When the first satellite of the system went up in 1977, the engineers reportedly built in a switch, a way to turn the relativistic correction on or off, half doubting it would matter. They ran the clock without the correction at first. Within hours, its drift matched Einstein's prediction almost exactly. They flipped the switch on and left it on. Relativity had already been caught in the act. In 1971, the physicists Joseph Haefel and Richard Keating flew atomic clocks around the world on ordinary commercial airliners, then compared them to identical clocks left at the United States Naval Observatory. The flying clocks disagreed with the ground clocks by exactly the few hundred nanoseconds that special and general relativity together predicted. Relativity sneaks in one more time. While a signal travels the 20th of a second down from orbit, the Earth beneath it has rotated a little. Accounting for that in a rotating frame is called the Sagnac effect, and it too comes straight out of relativity. Ignore it and you misplace yourself by tens of meters. GPS quietly corrects for it on every single fix. Relativity is the deepest correction, but not the only one. The signal also slows as it crosses the charged upper atmosphere, the ionosphere, and bends in the lower air. Modern receivers measure two frequencies at once to cancel most of that delay. Strip away every correction, relativistic and atmospheric, and the elegant blue dot on your map dissolves into useless noise. Keeping the whole constellation in agreement is a constant job. A network of ground monitoring stations around the world tracks every satellite, measures the tiny remaining drifts in its clock, and beams up corrections. The satellites are never quite left alone. Relativity sets the baseline. Relentless monitoring trims whatever is left to keep the system honest to the nanosecond. For its first 2 decades, the public never got the full accuracy. The military deliberately degraded the civilian signal, a policy called selective availability, leaving everyday receivers tens of meters off. Then, in May 2000, the United States switched the degradation off for good. Overnight, civilian GPS got 10 times sharper, and the modern world of precise navigation truly began. And it is no longer just an American system. Russia's GLONASS, Europe's Galileo, China's Beidou, every global navigation network now circling the Earth carries atomic clocks, and every one of them must apply the very same relativistic corrections. There is no way to build a working satellite navigation system on this planet without Einstein. The physics is not optional. GPS time, relativity corrected, accurate to the nanosecond, is the invisible heartbeat behind far more than your maps. It timestamps financial trades, synchronizes power grids, keeps mobile phone networks in step, and locks together the world's data systems. A huge amount of modern civilization is, secretly, keeping time by Einstein every second of every day, and some of what depends on this carries lives. Aircraft fly precision approaches guided by satellite, threading toward runways in poor visibility. Ships navigate narrow channels by it. Emergency crews find you by it. Every one of those fixes silently includes the relativistic correction, the 38 microseconds a day that, left uncorrected, would put the runway in the wrong place. Einstein is, in a real and literal sense, helping land the plane. Imagine you could flip a switch and turn Einstein off. The satellite's clocks would immediately begin to gain their 38 microseconds a day. By lunchtime, your position would be wrong by a few kilometers. By the next day, 10. Within a week, GPS would place you in the wrong city. The system does not merely benefit from relativity. It is built on it and collapses without it. This is what makes GPS so quietly remarkable. Relativity was once the most rarefied physics imaginable. Thought experiments about trains and lightning, light and falling lifts, with no practical use anyone could name. Within a single human lifetime, it traveled from the blackboard into orbit, and from orbit into the phone in every pocket. Pure theory became load-bearing infrastructure. So the next time your phone draws a little blue dot on a map and gets it right, remember what had to be true for that to work. A clerk in a patent office in 1905 and again in 1915 worked out that time bends with speed and with gravity. A century later, that almost unbelievable idea is the only reason the device in your hand knows where it is. Einstein never imagined satellites. He was chasing the deepest truth he could find about space and time, with no thought of navigation. And yet that truth turned out to be real enough and exact enough that we had no choice but to engineer around it. The universe does not bend to our convenience. The universe is not obliged to make sense to us. We measured how it actually behaves, and then we built the modern world on top of it. Somewhere above you right now, 31 atomic clocks are racing through orbit, each ticking at a rate Einstein's equations set, each watched and trimmed to the nanosecond. They will pass overhead tonight, silent and unseen, keeping a more perfect time than anything on the ground, the steady, relativistic pulse beneath the modern world. Most people will never know they are there.